All right, so let's go over the assigned problems from section 4.1. So we want to find a general solution to this second order homogeneous equation. So for the first one, I'll show kind of how this works or why this works. So essentially, we're going to make an educated guess that our general solutions are going to look like this form. They're going to take the form of e to the RT. So under that assumption, what would the first derivative look like? It would look like r e to the RT. The second derivative is going to look like r squared e to the RT. So now I can start substituting in these pieces for my differential equation. So I have r squared e to the RT plus 6r e to the RT plus 9 e to the RT equals 0. I can factor out e to the RT, and what's left is r squared plus 6r plus 9 equals 0. There's no way for an exponential to ever equal 0, so really all I'm solving is r squared plus 6r plus 9 equals 0. So that's why that characteristic equation, that's where that comes from. So now I have a quadratic. I can factor this to r plus 3, r plus 3. So I have a double root. So r equals -3. So I have a second order equation. So I want, there are going to be two solutions to it, and I want those two solutions to be distinct. And by distinct, I mean that I don't want them to be multiples of each other. I don't want them to be, constant multiples of each other. So how do I avoid that? Well, I'm going to call one of my solutions y1 of t equals e to the RT, so -3t. The other one is going to look like slightly different, e to the 3t. But like I said, I don't want it to be a multiple, but I do want it to, kind of be of a similar form without being a multiple. So we're going to multiply it by a single power of t. And if you want, you can check for yourself that if I take the solution and take the second derivative and the first and second derivative, it still satisfies our differential equation. Now, because of superposition, I have two solutions. I don't know whether the solution is only y1, only y2, or some combination of the two, some sum of the two. So here's what we have for our general solution. Some constant times e to the -3t plus some other constant times t e to the -3t. And based on the information I gave you, that is as far as we can take that. All right, moving on to 18. All right, so initial value problem. So the constants we just left unevaluated, we can evaluate in this question. So let's jump ahead to the characteristic equation because that's going to be a step that is common to all these. So r squared plus 3r minus 10 equals 0. This should factor into what? -2 plus 5, I believe. R minus 2. R plus 5 equals 0. So I get r equals -5 and +2. All right. Which means my solution looks like what? I have x of t equals c1 e to the -5t plus c2 e to the 2t. All right. So we have enough information to figure out those constants. So let's go ahead and plug in our initial values. We know what x of 0 is, and we know what x prime of 0 is. So x of 0 is, that's just going to be c1 plus c2, because we plug in 0 for t, those exponential terms just become 1. So C1 plus C2 equals 1. All right, to figure out to go forward, we have to figure out the derivative. So x prime of t will be negative 5c1 e to the negative 5t plus 2c2 e to the 2t, and evaluate that at 0. So I get negative 5c1 plus 2c2, that equals 2. All right, so now I have a system of 2 equations, 2 unknowns. Lots of ways to attack those. I'm going to go ahead and use elimination. I guess I'll go ahead and do that now. I'm going to go ahead and multiply this equation by 5. So 5c1 plus 5c2 equals 5. And then I'll just write my other equation below it. Negative 5c1 plus 2c2 equals 2. And what do I get here? I get that 7c2 equals 7, which gives me that c2 equals 1, which I believe also tells me that c1 equals 0. So even though we accounted for both solutions here, given my initial conditions, I think we have learned that one of those solutions has no impact. It has, no bearing on the solution. So we have x of t equals essentially 0 e to the negative 5t plus 1 e to the 2t. All right. So next. All right, so now we're looking at a harmonic oscillator. So essentially what we're modeling is this. I have a table, and there's, a mass on a spring. That spring is anchored, to the wall or something else. So what forces are acting on this spring? Well, one is going to come from, actually, well, let's not discount them. There's going to be a force of gravity, and there's going to be a force of reaction from the table. But those are going to cancel each other out. The only net forces we're going to have on this mass are going to come from what's acting horizontally. So we're going to have a force that's acting from the spring. And we're going to have a force that's acting from the damping coefficient. So, and those two forces added together are essentially going to, that's going to give me a net force, and that's going to dictate how this block accelerates. So we know from Newton's second law that the sum of all forces equals mass times acceleration. So what is the sum of all forces here? So as this thing moves, let's say it's moving to the right. And just to kind of, in the name of consistency, we'll say to the right is positive. If it's moving to the right, then I'm going to have two forces acting on this. One force is going to come from Hooke's law, which is sigma F. So Hooke's law is given by negative kx. So basically, the higher k is, the stiffer the spring is, the harder it is to compress or extend the spring. The reason I'm saying negative is because that force always acts in the opposite direction of, however the spring is deformed. If you've compressed the spring, then the spring will want to extend, and vice versa. And then how does the damping coefficient work? It basically works the same way. If the object is moving to the right, it's going to, basically the damping coefficient is going to push it back. It's going to impede that motion. So in this case, that force is also going to be negative. So minus BV. All right, so my sum of all forces is equal to mass times acceleration, which is also equal to minus kx minus BV, which I can write this thing as a differential equation because what is x? X is essentially how far from the equilibrium position I am, deforming my spring. So that's position. What's velocity? Velocity is a rate of change of position over time. And what's acceleration? That's a rate of change of velocity over time, or the second derivative of the rate of change. Sorry, the second derivative of position with respect to time. So I'm going to rewrite this way: mx double prime equals negative kx minus bx prime. And to make this thing a true homogeneous solution, I'll move everything to one side. Mx double prime plus bx prime plus kx equals 0. So just a little background on where this thing comes from. It all comes from the net force, Newton's second law, basically. What's the acceleration acting on this block? So now we can fill in the details we were given. We know that the mass is 2, so 2x double prime plus 3x prime plus 5x equals 0. Okay, so write the second order initial value problem corresponding for the harmonic oscillator. So we essentially have it. This is the differential equation. We wanted the horizontal, or one of the initial values. So we know that x of 0 is 2, and we know that x prime of 0 is negative 1. All right, so that's done. Part B. All right, for part B, classify the oscillator as undamped, underdamped, overdamped, or critically damped. So that comes from the discriminant, essentially. So let's find the discriminant of our characteristic equation here. So our characteristic equation is going to be 2r squared plus 3r plus 5, which means our discriminant is going to be 3 squared minus 4 times 2 times 5, 9 minus 40, which equals negative 31. So that is imaginary. So when we have, so we're not going to have any real roots to our characteristic equation. And in that case, we have an underdamped solution. So, which means when we solve this problem, we should expect to see a response that oscillates. It's not just going to monotonically go towards rest. All right, next, we're going to solve this problem. So we've written a homogeneous second order differential equation. How do we solve these things? No different from the other ones we've solved. All right, so we want to solve this characteristic equation. Don't believe it factors, so we'll use the quadratic formula. R equals negative 3 plus or minus the square root of b squared minus 4ac all over 2a. So I get negative 3 plus or minus The square root of negative 31. So I radical 31 over 4. So what do my roots look like? I get e to the negative 3 plus radical 31 it. I'm just going to keep 1 because in the case of complex roots, 1 is sufficient to give you everything you need. So I'm going to use Euler to break this down. First, I'll break it down like this. So this becomes e to the negative 3t times e to the radical 31 it. And this second part that contains the imaginary operator, what does this become? So e to the negative 3t times cosine radical 31t plus I sine radical 31t. So we know that our complementary solution, our solution is going to have the form of an exponential term times a cosine, and our other one's going to have a form of an exponential term times a sine. So we'll go ahead and write that out for now. So recline x of t equals c1 e to the negative 3t cosine radical 31 t plus c2 e to the negative 3t sine radical 31t. In case you're wondering why we did not carry the I, the imaginary constant, there are several reasons, but one that is always going to be ring true for us, no matter what kind of equation we're looking at, is that if we have an equation whose coefficients and values are real, our solutions have to be of the same type. They have to be real valued with real coefficients. All right, so here is our here's our differential equation, or sorry, here's our particular solution. So let's now work on evaluating those constants. So what is x naught, or x of 0? That should be equal to c1 times 1 times 1 plus c1 times 1 times 0. So I should get c1 for free. So c1 equals 2. Okay, so that's one constant. So for now, I'm going to go ahead and do this. It's not unknown to me anymore. I'm going to go ahead and drop it in, which should make my life easier in finding C2. So first, I need to figure out the derivative. So what is x prime of t? I'm going to need to use the product rule for both of these. All right, so this should be negative 6 e to the negative 3t cosine radical 31t plus 2, minus 2. Minus 2 e to the negative 3t sine radical 31t. I'll go to a new line to handle the other part. Minus 3c2 e to the negative 3t sine radical 31t plus c2 e to the negative 3t cosine radical 31t. And now I'm going to plug in 0 for all that. And all that should survive should be the cosine terms. So negative 6 times 1 times 1, so negative 6, minus 2, sine term, sines go to 0, sines go to 0, plus c2 equals what? -1, which means that C2 equals 7. So now we got our full solution. X of t equals 2e to the -3t cosine 30 radical 31t plus C2, no, I'm not calling it C2, no, I know what that value is. 7e to -3t sine radical 31t. All right, so that is my particular solution for C. All right, finally, I want to sketch these curves. So let's go ahead and back out of here. Let Desmos do that for us. All right, so that should be it. So like we said, that we have an underdamped response, so we should have, it should eventually trend towards rest, which it kind of does. Actually, this does not show speed. This shows position. So let's confirm our initial values. F of 0 equals 2. Our velocity at time 0, oh, that doesn't match. So let's go back and try to debug that. Did I do my derivative correctly? Oh no, I got all kinds of chain rule stuff that I missed out on. So let's go back and take care of that. So my derivative, let's just revisit the whole derivative. So -6 e to the -3t times cosine radical 31t minus 2e to the -3t times sine of -30 or radical 31t times radical 31. Minus 3c2 e to the -3t times sine of radical 31t. Right, I think so. It's these two terms that require radical 31. So how did that filter forward? So x naught, all the sine terms go away. So it should be this. Oh, I can't erase that anymore. -6 plus radical 31 C2 equals 7. Oh no, it equals -1, huh? So C2 should equal, oh, I did all kinds of stuff wrong. It should be 5 over radical 31. Let's try that. Okay. Now things match. Okay, so glad we checked that because I was totally wrong. Okay, so now we get the response that at least it matches initially. All right, so that is all for the questions from this section.